Okay, so in this problem, we have a deep shaft and the surface temperature, which is the cold reservoir, is at minus 40 degrees C. And let's put that into kelvins. So that's 273 minus 40, which is equal to 233. And then we've got a hot reservoir, which is at 800 degrees C, and again we'll put it into kelvins. So 273 plus 800 gives us 1073 kelvins. And in the first part, we're asked what is the theoretical limit to the efficiency of the engine at these temperatures. Okay, so the most efficient engine we can have is the Carnot engine, which has an efficiency of 1 minus TL on TH. So that's equal to 1 minus 233 over 1073. Solving that on the calculator, we end up with 0.783, which is equal to 78%. So theoretically, that's the most efficient one. Part B. Okay, part B is really very difficult. It tells us if all the energy released as heat into the low temperature reservoir. So is the energy released as heat to the low temperature reservoir, so that's QL, is used to melt ice. Okay, so we're going to need to find QL. And the ice was initially at 40 degrees C. So the temperature initial for the ice is minus 40 degrees C. At what rate could liquid water, so because it says at what rate could, we're going to assume the maximum efficiency here. So could liquid water at 0 degrees C be produced by a 100 megawatt, so the power, which is equal to the energy over the time, is 100 megawatt power plant, which we treat this as our engine, so this is going to be doing the work. So this will be equal to our work over time. The specific heat of ice is equal to 2,220 joules per kilogram per Kelvin. And the latent heat of fusion is equal to 333 kilojoules per kilogram. And useful note, the engine can operate only between 0 degrees C and 800 degrees C in this case, because energy exhausted at minus 40 degrees C cannot warm anything above 40 degrees C. Okay, so that's going to be a limit on our efficiency in this case. So the low temperature in this case is going to be 0 degrees C, which is equal to 273, whereas our kelvins, whereas our high limit is still 1073 kelvins. Okay, so from reading the question, we knew that we needed to try and find QL, the amount of heat released to the lower reservoir. So one way we can do this is to consider the efficiency. We know that the efficiency of an engine is equal to the work it does over the energy, the heat it releases to the high temperature reservoir. But we know the relationship between this and the heat released to the low temperature reservoir, because we know that around a cycle the work done is equal to the heat absorbed, and so this is equal to QH minus QL. So what we can do now is replace QH here with W plus QL. So our efficiency is equal to W over W plus QL. And so what we're trying to do is find QL. So we can rearrange this. We end up with W plus QL is equal to W over the efficiency. And so this tells us that QL is equal to W outside of 1 over the efficiency, and then we're subtracting this W from that side, which we've pulled out the front, so it's equal to this. Okay, now we also know that our efficiency is given by this, so we can write this if we want, as TH minus TL on TH. And this we can then substitute in here, because this then tells us that QL is equal to W, and what I'm going to do is replace 1 on the efficiency with TH over TH minus TL. We'll give this a common factor down the bottom. Okay, so now we end up with W, TH minus TH cancels out, so we end up with TL over TH minus TL. Is one expression that we can have for QL. But we also know that this QL is used to melt the ice. And to melt the ice, first of all, it needs to raise it up to melting temperature. So the final temperature, this is 0 degrees C. The ice starts at minus 40 degrees C. And then it also needs to melt it. So it needs to make the mass of ice undergo this phase change. So that's times mL. So this is what that heat is used for. Okay, and what we're trying to work out is what's this mass per second. Okay, so let's just pull mass out as a common factor, because that'll be a bit useful later. So this is C times change in temperature. So that's the change in temperature of the ice. So let's put a little subscript ice so that we remember that, plus L. Okay, and we know that this is equal to the work done over TL over TH minus TL. Okay, now what we want is the mass over the time. Let's divide this through by here, and we've also divided by time. So we'll have this is equal to the work over the time, because I need to divide both sides by time. I've still got this here, so this is TL over TH minus TL. And then I'm dividing by this. So this is 1 over C times delta T ice plus L, and there's brackets around that. Okay, now why I've done this divide by time is not only because I wanted the rate of the weight change, so a rate is divided by time, but also the work divided by time, that's our power. So we have that number, it's 100 megawatts. So now we actually have all the numbers, so we can just substitute in now. So this work over time is 100 times 10 to the 6. The 10 to the 6 is because that's a mega. Okay, TL, we were told with this one it could only go between 0 degrees C. So TL is 273. This is 10,073 minus 273, which should give us our 800 back. This is 1 over C, which we were told was 2,220 joules per kilogram per Kelvin. That's all SI units, times delta T, that's the change in temperature of the ice. So as it got from minus 40 degrees C up to its melting temperature. So that's 40 plus L, which is 333, and that's kilojoules per kilogram. So we times it by 1,000 to get it into joules per kilogram. And putting this into the calculator, we end up with 80.9, which we can write as 81 kilograms per second.